All right, so in this lecture, we're going to talk about NumPy. NumPy is an external or third-party library, meaning it's not part of the standard Python installation. It can be installed a various number of ways. All of them are pretty straightforward and easy, but nevertheless, it's a third-party library for doing numerical computations. That is, array operations or operations on arrays of numbers. You might have heard that Python is slow, and part of the reason that Python in its pure form, pure implementation, pure Python, not using a library like NumPy, is slow is because of something called quickly called duck typing. So if it looks like a duck, then it is a duck. That means if a variable looks like an integer or a float or a complex number, then the runtime engine, when Python executes the code, it treats it as such, what it looks like. And this causes a lot of overhead at runtime, trying to determine what type of a variable is. And the solution for that is to use so-called NumPy data structures. So these are data structures as objects, right? We know a little bit about object-oriented programming. So these are data structures as objects that have a single type and contiguous storage. So contiguous storage meaning all the data lays next to each other in memory. And this can be important for minimizing cache misses and other low-level performance issues. It's implemented in C, and if you're careful in the use of NumPy, you can actually expect near C-like speed in performing computations on the entirety of an array. So let's look at an example of kind of how slow Python is, or a comparison to NumPy. And to do that, we're going to use the built-in timeit function from IPython that's built into Jupyter notebooks when you're using a standard IPython kernel. So what we're going to do here is we're going to use a Python list comprehension to add 1 to a million numbers. So this range function, of course, will give us 0, 1, 2, 3, 4, 5, all the way up to a million. And we're going to use this list comprehension to add 1 to each of those numbers in succession and store the result in a list. And so if we do that on my computer here, you'll see that it winds up with 131 milliseconds. So if we do the same operation in NumPy, by the way, we import NumPy as the standard way to import NumPy is to import NumPy as NP, and then we use the NP namespace to create an array of numbers that go to a million, and then we just simply add 1 to those. And NumPy is smart enough to cast this +1 operation across that array of numbers. And so they perform, if you were to view the output of these arrays, you'd get identical answer. And in this case, you can see it's something like 100 times faster to do it in NumPy. That is, again, on my computer. The real key here is not the absolute speed, but the relative difference between the two numbers, right? This NumPy implementation is much faster. So NumPy also gives us something called universal functions. These are vectorized functions that operate on arrays in an element by an element fashion. So if we wanted to say take the sine squared of each number, again up to a million, to do that in Python we have to basically put it in a loop or a list comprehension like we've done here, and we individually take the sine of each number and then store those values as we go over the list. We can, however, do this in NumPy like so. So we have a function sine that's defined for NumPy arrays. When we stick an array, in this case, again, 0 to a million integers in this array, it will take the sine of each element individually in an element-wise fashion. Again, also squaring those numbers here. So again, the result of these two operations would be identical, but the NumPy version is much faster. There are many ways to create arrays in NumPy. We can start with a Python list if that list is initially given as a list of integers, then the resulting NumPy array will also have the type integer. If we were to basically use the decimal point in any of those numbers, then we would get an array of doubles. Or if we were to use this special syntax for complex numbers, we would get an array of complex numbers. So in this second example, it is an array of complex numbers. We can also create a range of numbers. So in this case, it would go from -10 to 10 in steps of 2. And even though we use what look like integers as inputs here, we can be specific about the data type. And a lot of times I'll do this for readability, is be very specific about the data type. So in this case, the data type is a float, which is a single precision 32-bit floating point number. We can create a linear space. So in this case, it would be a set of doubles, floating point doubles, that go from 1 to 4, and there would be 6 of them equally spaced in between. And we can also read data from a file, like so. So there are other ways too to create arrays, but these are the kind of most common ways to create them from Python lists or specify an A range or linear space. So NumPy has an array of utilities or many utilities for getting information about arrays, slicing, other things. In fact, the slicing notation in pure Python actually was borrowed later on from the NumPy slicing notation. So if we start here, we can create an array. This will be just a list of integers from 0 to 9. We can call this function reshape on it, which will take the one-dimensional array that was originally created, and it will reshape it into a 3 by 3. So it looks like a matrix in this point. And you can see the numbers 0 to 8 there. If we wanted to get a part of that array, we could do it with this type of notation. So the colon means take all, in this case, rows, all of the first dimension. And so this means take all of the rows in the 0th column, or the first column, right? So in that case, 0, 3, 6, that would return that part of the array there. Again, NumPy arrays are objects once they're instantiated, so they have attributes. In this case, one of the attributes is shape, and when we call reshape on it, we're actually changing that attribute. So the array or the object is stored in X, and it has an attribute shape, which tells us it's a 3 by 3. We can reassign parts of arrays using this kind of notation. So the syntax here is, again, along the first dimension of X, go from the beginning to the end in steps of 2, and along the second dimension of X, go from the beginning to the end in steps of 2. And so that's what we do here. We'll say in steps of 2, we'll take 0, 2, and then in steps of 2 along the rows, we take 0 and 6, and then 6 and 8 along the columns. And so that gives us Y there, this little piece of our original X. And we can actually use this to reassign parts of the array. So in this case, we want to reassign the 0, 0 entry to 100. We would have this type of output. Now here's something that you might not expect, is if we look back at the original X, so remember Y was assigned to a piece of X. And when we changed Y, we also changed X. That's because X, or Y rather, is just a view into X, okay? It was not a complete copy in memory. It's just a special view into that part of X which we assigned here. So any changes to Y will also change X when done this way. And this is just you have to be careful and know about this functionality because it could catch you if you expect that Y is a copy and that you want to leave X unchanged. If you want to actually do that, what you should do is make what's called a deep copy. So in this case, we're explicitly going to call the copy method after making the reassignment to the part. And in that case, then, if we reassign part of Y and then look at what X and Y are, we see that X remained unchanged, as we made this assignment to the 0, 0 entry of Y equal to 200. Another thing we can do is very efficient and compact finite differences. So from the definition of a derivative, so say we have a function f and we want to know how it changes with respect to x, then we can approximate this, right, from, the limit, say as delta x goes to 0. I'm just essentially rewriting the definition of a derivative. Like so. Of course, the definition of a derivative takes this limit here. However, in the discrete case, we can't actually take delta x all the way to 0, although we can approximate it to be very small. So this is an approximation of the derivative, okay? And so what we can do with this is if we take, say, for discrete data where this might be xi, a point xi, and we'll call this xi plus a half, where delta x I plus a half is simply simply x at I plus 1 minus x at I. And if we imagine we have some function that's smooth, but we discretize it at individual points, and then we give these points a label, say call this one xi and this one xi plus 1, then an approximation to the derivative here, this line, could be taken with this formula here. By evaluating the function at xi plus 1, well, what we can do is we'll call this distance delta x, right? So this is xi plus 1 is the same thing as saying f at xi plus delta x. So we'll evaluate the function at this point, subtract the evaluation at that point, divide by delta x, and that gives us approximation to the slope at this line. Of course, the approximation becomes more accurate as delta x is smaller. We can do this in NumPy very efficiently in a compact way. With this type of operation. So in this case, we have an array x, that's just a discrete set of numbers that go from 0 to 40 in increments of 2, and then we'll square that to get y. So, and we want to compute the derivative of y with respect to x. What we'll do here is, using this syntax, this computes all of the changes in y across the whole array. So starting from the second element of y to the end and subtracting from the beginning of y to 1 from the end, that gives us our delta y, and same thing for our delta x in the denominator here. And so then the resulting, the approximation to the derivative of the curve is that. And if we plot this, then you can see, so our original y of x is this black line, and if we compute the derivative, these numbers right here are actually plotted against x in this red line here. And of course, we know that the slope or the derivative of x squared is 2x, and if we were to evaluate the slope of this red line, we would see that it is in fact 2. We can do more sophisticated so-called broadcasting. So earlier we saw how we could broadcast the sine function or broadcast the operation of adding 1 across an entire array. We can actually do complex broadcasting against multiple dimensions in an array. So here we're going to start with 3 dimensions. We'll call red, blue, and green. Each of these are 2 by 2 arrays. Each of these are 2-dimensional arrays, 800 by 600 in each of those. We're going to use those 3 arrays to create another dimension of an array we'll call RGB. And so if we look at the shape of RGB, it is 3 by 800 by 600. We can then transpose that array to make it 800 by 600 by 3. And so the outer dimension is then 3, and we can multiply by a 1 by 3. So in this case, we'll multiply by a half, and a quarter. And that multiplication is broadcast against the whole array. So all of these individual, the red is multiplied by a half, the blue is multiplied by a half, and the green is multiplied by a quarter. Here's the resulting array, which is hard to visualize, but an easier way would be to actually look at the images that are created if we consider those red, green, and blue values to be color values of a pixel. Our original image looks something like this, and our scaled image looks something like that. And we can see that it's more green because we had more influence from the green component coming in the scaling. We can also do something called fancy indexing. So with fancy indexing, we'll start with this original array x we call like this, and we've already seen that if we wanted to take the component of x, the third index, so 0, 1, 2, 3, we would call it like this and would return the value there. This is no different than a Python list, of course. But what we can do with a NumPy array that we can't do with a Python list is we can do this so-called fancy indexing. So if we wanted to take various numbers from the array given in a list, so the 0th component, the 3 component, and the -1, which indicates 1 from the end of the array, then we can do it in this way, right? So again, we get just the 0, the 3, and the last one, which is 8. So this is called fancy indexing. If we notice, we cannot do this with a pure a pure Python list. So a Python list, if we just create it here, 1, 3, 5, 7, we don't wrap it in NumPy array or anything like that. We have a pure Python list. If we tried to take just the second and third components of that list, then we would get an error. This fancy indexing works for multiple dimension arrays. So if I reshape x into a 3 by 3, set that equal to y, and then take the 0th component, that would mean to take that would take the 0th row, right? So the entire row here, 0, 1, 2, and that's what we get. And we can also do it in multiple dimensions. So we can take the first and second row, right? So the 1 index and 2 index row, which are the last two. And we can also even get fancier than that and take the 0, 1, 2 component, or I'm sorry, the way you would read this would be the 0, 0 component, the 1, 1 component, and the 2, 0 component. And that's what we get here. So, right, 0 is the 0, 0 component, 4 is the 1, 1 component, and 2 and 6 is the 2, 0 component. Right? So that's how we read that kind of thing. We can also have Boolean arrays. These are very convenient. So what we'll do is just start with a group of random integers. And then we can actually set a condition, right, to say that wherever x is greater than 0, then return the element-wise conditional statement, right? So wherever x is greater than 0, that is wherever x is a positive number, it will return true. Otherwise, it will return false, right? And so you see that you can compare, right? 1 is positive, true. 6 is positive, true. 3 is positive, true. 2 is positive, true. -4 is negative, false, right? And so on. Then we can take this index array, which I've set to the value index there. I can take that IND array and use it to actually fancy index back into x to extract the actual numbers. So if I wanted to get the positive numbers from the array, then I could do this kind of operation. So we use this often in like cleaning data and other things, or truncating data. There's also a convenient function called ware, which basically allows you to say, where true, right? So where index the array is true, then in that case I want to return those components of the original array x. And otherwise, I'm just going to return string, right? This is kind of a contrived example, and you'll see, because the data types in NumPy have to be contiguous, it converts the whole entire output array to a string. So these 1, 6, 3, 2, those are the actual string value. Those are actually strings, not numbers anymore. But nevertheless, it just shows the kind of things you can do. So again, the syntax here is where IND is true, return those components of x, otherwise return something else. And you could, change this to say return 0 in those cases. And that's, you get a different answer, right? So in this case, where true, you'd get the numbers, and otherwise you'd get 0. So the second argument is kind of like the otherwise in an else statement or else if statement. So that's a brief overview of NumPy.